This is the fourth oscillations lecture. In this lecture we're going to be looking at lots of important things. We're going to be looking at wave speed, reflection, transmission and the superposition of waves.
This lecture will be covering sections 16.2 to 16.5 of your textbook.
First of all, a quick recap of the most important ideas from last lecture. We saw that transverse waves were ones in which the particles that make up the medium oscillate in a direction perpendicular to the direction that the wave is travelling in. In longitudinal waves, the particles oscillate in the same direction that the wave travels. We saw that a pulse travelling to the right has a wave function y of xt is equal to some function of x minus vt. This minus comes about as it's travelling to the right in the positive direction. We went over some definitions for waves, which you probably saw in high school. The amplitude of a wave is the distance between the equilibrium position and the crest, or the trough. So it's 2 times the distance between the crest and the trough. The wavelength is the distance between 2 crests along the length of the wave. The period of the wave is how long it takes in time for one crest to pass you and then the next crest to pass you. The frequency is the inverse of the period, and the velocity of the wave is equal to f lambda. This is a very important equation for you to know. Last lecture we also showed that the form of the wave equation was y of xt is equal to a sine kx minus omega t plus phi. The k is the wave number. It's not related to the spring constant. It's equal to 2 pi over lambda. The negative sign here indicates that it is travelling to the right. If the number in front of the x and the t have the same sign, it's travelling to the left. If they have opposite signs, it's travelling to the right. Omega is the angular frequency. It's equal to 2 pi f. And phi is the phase constant, which lets us match this wave up with our initial conditions. This is a transverse wave, as this displacement is in the y direction while the wave is travelling in the x direction. We're now going to derive a formula for the speed of wave on the string. Here's the pulse that we're going to be considering is travelling from the left to the right along the screen here. Now imagine yourself in the reference frame of the pulse. So you're travelling along at the top of the pulse here. You're this increment delta s. What you see is increments of the rope going past you. They'll be travelling to the left. Okay, now let's consider what's happening in this case. Delta S is a little arc length here. R is the radius of our semicircular hump. Theta is the angle between the middle of our arc length and the edge of our arc length. So the total angle in here is 2 theta. So from our equations for arc length, we know that the length delta S is equal to 2r theta, because the angle is 2 theta and the radius of our semicircle is r. Now we're going to have a think about all the forces acting on the system. We have tension pulling the string down in this direction. We have tension pulling the string down in that direction. Those are the 2 forces acting on it. And the result is that this undergoes circular motion. And so the resultant force is equal to mass times the centripetal acceleration. This makes the geometry a bit more clear. The tension is pulling on the end of this increment down here and on the end of this increment here. Because the radius makes an angle of 90 degrees with the circumference of the circle, this is 90 in here. So this angle in here is equal to theta. Okay, so that's just the same picture again. Now what we do is we move this tension here, so that we're adding them head to tail. When we do that, we know that our resultant force is the mass times the centripetal acceleration. So looking at the geometry, this angle in here was theta, which tells us this angle here is theta. So half the length down here is t sine theta. So the length of this resultant force is 2t sine theta. So that's why we've got this 2t sine theta here. And here is our centripetal acceleration. Now we're going to make the small angle approximation. If theta is small, then sine theta is approximately theta, so we can replace this sine theta here with theta. That's what we've done here. Now what we need to do is work out this mass here. So the mass of a piece of string is equal to the density per unit length of the string times the length of the string. But we've already shown that the length, delta S, is equal to 2r theta, because it was the arc of that circle. So we can say that the mass of the piece of string is the linear density times 2r theta. So now we're just going to substitute that in. Here's our resultant force, 2t theta, and here's the m v squared on r term, and m's been replaced with this expression here. Now there's lots of things we can cancel out. We can cancel out our thetas, we can cancel out the 2's, we can cancel out the r's, and when we do that, we're left with the expression T is equal to mu, the mass per unit length, times the velocity squared. So we can rearrange that to write that the velocity is equal to the square root of the tension over the mass per unit length. Now you'll be using this formula quite a lot, and this will come up in the standing waves on a string experiment in the laboratory. To practice using it, you should try homework set 5. For 1121, try problem 13. 1131, try problem 17. Now, we assumed that this was a semicircular pulse. It actually turns out that the shape doesn't matter. Any shape can be approximated as a semicircle at the very top. So actually the pulse shape or the wave shape is unimportant. This equation holds for any wave shape. Now we also assume that the tension T along the string was constant, so that this pulse travelling along the string was not affecting the tension. That's only true if the pulse is fairly small. If the pulse is very large, then it's going to cause the string to stretch, and that's going to add some extra tension. We'll see later that this equation can actually be generalized. We'll be seeing it for sound waves, but we can actually generalize it to the velocity is equal to some elastic property, in this case the tension, over some inertial property, in this case the mass per unit length. For a sound wave, it ends up being the bulk modulus, given the symbol B, over the density of the per unit volume of the material that the wave is travelling through.
Here's an easy question to practice using this formula.
A uniform string has a mass of 0.3 kilograms and a length of 6 meters. The string passes over a pulley and supports a 2 kilogram object. Find the speed of a pulse travelling along the spring. Okay, so we're going to be using our equation V is equal to the square root of T over mu. Now, first of all, we need to work out what T is. In this case, we had a 2 kilogram mass. It has a weight force downwards, and it's this weight force which is generating the tension force in the string. So the tension force is equal to the weight force, which is 2 times 9.8, so that is 19.6 newtons. Now we need to work out the mass per unit length. We're told that the mass of the string was equal to 0.300 meters and the length was 6 meters. So the mass per unit length is 0.300 over 6. Solving that gives us 0.0500 kilograms per meter. So now all we need to do is substitute into this formula. We end up with V is equal to the square root of 19.6 over 0.0500. Solving that gives us 19.8 meters per second. So that is the speed of the wave along this string.
Now we're going to consider the power transmitted by a wave travelling along a string. So we're going to start from the formula for kinetic energy. I'll show you this derivation in just a minute. We're going to end up with the power is equal to a half mu, where this is the linear density, v, that's the wave speed, omega squared, the angular frequency squared, times a squared, which is the amplitude squared. So let's derive this formula now. So we need to start from our expression for kinetic energy. We know that kinetic energy is given by, well, dk, that's for an increment of kinetic energy, is given by a half dm times u squared. Now this is for an element of string. So this speed here is not the speed of the wave, it's the speed that the piece of string is moving at. So in order to work out how quickly the piece of string is moving, we're going to need to use y of x and t is equal to a sine kx minus omega t plus phi. And then we can differentiate this to find out how quickly a piece of string is moving. So u is actually equal to dy dt, which you can see is equal to, in this case, minus omega a cos kx minus omega t plus phi. Okay, so now if we want to find out how much kinetic energy in an increment of string, we've got dk is equal to a half. Now the mass of a small piece of string here, we can give it a mass. If it's got a length dx, then dm is going to be dx times the linear density, which is mu. So we can write this dm as mu dx. And now we've got u squared, so that's omega squared a squared cos kx minus omega t plus phi. Now because we're trying to get power, which is energy divided by time, let's work out how much of this energy flows through in a tiny increment of time. So we're going to divide by dt now. So we've got dk dt is equal to a half mu. Now we'll actually divide this dx by the dt. Doesn't matter which term we divide, but you'll see why we choose this one in a minute. Omega squared a squared cos, well, this should be squared kx minus omega t plus phi. And now dx dt, that's how quickly this wave is travelling in the x direction, so that is v. So that is equal to a half mu v omega squared a squared cos squared kx minus omega t plus phi. Now what we really want to do is work out what's the average value of this dk dt. So if we want to work out the average value of the dk dt, we're going to need to know the average value of cos squared of something. So it is a half. If you want to work out what it is, one way to do it is we can integrate from 0 to 2 pi of cos squared theta d theta, and then we have to divide by 2 pi because that's the range, this range, 2 pi. And when we integrate this thing is pi, so this is actually equal to a half. So that's one way to show that this cos squared, the average value of that is a half. So we have that dk dt average is equal to a half times a half, so that's a quarter mu v omega squared a squared. So we've now worked out how much energy is transmitted as kinetic energy. However, the string has also got potential energy, and the potential energy with sine and simple harmonic motion gets converted between, well, the energy gets converted between kinetic energy and potential energy, and on average these two things have the same value. So that tells us that P is equal to dk dt plus du dt, and we can take the average of both of these, and these are the same, so this actually turns out to be equal to a half mu v omega squared a squared. So we've now shown the relationship that we set out to prove.
So what we're going to do now is derive an equation called the wave equation. This is a second order differential equation, which is d squared y dx squared is equal to 1 on v squared d squared y dt squared. This can be applied to all waves. Applying it is a bit beyond the scope of this course, but it's important that you see this derivation. So we'll cover the derivation now. So we're going to imagine a wave travelling along a piece of string like this, and so these two forces here are both tensions pulling on the string, and at this moment the string is being accelerated upwards.
Okay, so looking at this, we can say that the magnitude of F2 is equal to the magnitude of F1 because these are both equal to the tension in the string T. And now to derive this wave equation, we're going to start with Newton's second law. So we're going to start in the y direction. We know that f2y minus f1y is equal to ma. In this case it's dm because it's a small mass on this increment times ay. So that's just Newton's second law. And now we know that because it's a string, dm is equal to mu dx, and we know that ay, that's the acceleration in the y direction, so that's d squared y dt squared. So now what we're going to do is we're going to look at the slope of these lines here. So the slope of the string is really the same as the kind of slope of the force, if you like. So let's say S2, that is equal to F2y over F2x. So we can think of this as a rise over run or a slope. You'll see why we do this in a little bit. And then S1 again is F1y over F1x. And so now we can call the difference between these two slopes, S2 minus S1, is equal to ds. This ds is a very small number because this wave is travelling along the string, so we've got almost the same slope there as there. Okay, so now what we know is that F2, this second force, is been broken into two components, y and x, and so Pythagoras' theorem tells us that this is F2x squared plus F2y squared. But also because this is a pulse travelling along a string, we know that the displacement of the pulse can't be large compared to the string. So we know that F2y is a lot less than F2x. So this is approximately equal to F2x, which we can also call equal to, looking at this equation up here, this is equal to F2y on S2. Now we can do the same thing for F1. F1 is approximately equal to F1x, which is equal to F1y on S1. So now using that F2 and F1 have the same magnitude, let's substitute into this top line up here. So F2y is equal to F2 times S2. F1y is equal to S1 times F1. So S1, F1. But what we're going to do is replace this F1, because it's got the same magnitude as F2, with an F2. So there we go, there's our F2. And this thing is equal to this thing, which is the mu dx, times d squared y dt squared. Okay, now S, we said S was the gradient, so S is equal to dy dx. So what we've got here is F2 ds. So let's put this as ds, which is equal to mu on F2. Now we're going to move this dx over to the other side, so there's the dx times d squared y dt squared, which tells us that S, this is d of dy dx, so that'll be d squared y dx squared is equal to mu over F2, which is the same as the tension, so let's put the tension there, d squared y dt squared. Now previously we've shown that the velocity is equal to square root of tension over mu, and so we've got v squared is equal to t on mu, so we can replace this mu on t with 1 on v squared. So we've got d squared y dx squared is equal to 1 on v squared d squared y dt squared. And so that is how we derive the wave equation.
Okay, now we're going to consider the reflection of the pulse. Imagine a pulse travelling along the string and it comes to a fixed end. Now at this fixed end, the pulse applies a force upwards on the support, and so according to Newton's third law, the support will apply an equal and opposite force on the pulse. So when the pulse is reflected here, it is reflected underneath like this. We say that it undergoes a pi phase change. Now if the pulse is reflected from a loose end, so for example it's tied onto this ring which is free to move, then there won't be a force pushing it down, so it's not going to be inverted when it's reflected from a loose end like this, and so it travels back along the top of the string. Now when a pulse reaches a junction, some of it's transmitted and some of it is reflected. So in this case, when we're going from a less dense medium to a more dense medium, it's like it's being reflected from a fixed end. So the reflected wave undergoes a phase transition of pi radians, and the incident pulse keeps on travelling through the high density medium. When the incident pulse travels from a more dense medium to a less dense medium, it's like being reflected from a loose end, and so it doesn't undergo that phase change, it isn't flipped over, and here it continues to travel along the string. When it moves to a less dense medium, it ends up going faster as mu is smaller. So as a wave moves from one medium to another, its velocity will change because the different mediums will have different tensions and different density per unit length. Its frequency remains the same. So its wavelength must change because we have v equals f lambda. If the velocity is changing and the frequency is staying the same, then lambda must change. So slower waves in more dense mediums have a shorter wavelength. If this is smaller, then this is smaller. Now often there is more than one wave travelling through a piece of string or other medium. Often you will find the reflected wave and also the original wave are travelling through the same medium. So this brings us to the principle of superposition, how we deal with adding two waves together. If two or more waves are moving through the same medium, the resultant value of the wave function is the algebraic sum of the wave functions of the original waves. Two waves can pass through each other without being destroyed or altered. So we're going to see how we use this to solve some problems. First of all, imagine these two waves travelling along a string. This is the snapshot of the two waves at a certain point in time, and now we need to add them together. All we need to do is at each distance along the string, add the amplitude of the two input waves. So initially they're both at 0. So our superposition is going to be at 0 initially. Now at this point 2, this wave's at a maximum, this one's not that much more, so we have the addition of these two here. Now at around about 5, we have this wave is negative and this wave is positive, so at that point they cancel each other out. When one's positive and one's negative, we end up with a very small amplitude. So these diagrams just show you constructive and destructive interference. When the pulses overlap and sum together to give us a positive amplitude, then we call that constructive interference. When the pulses are on opposite sides of the string, then instead of adding, they subtract from each other, and we end up with a smaller resultant pulse, and that is called destructive interference. So quantitatively, let's consider two sine waves that are identical apart from their phase travelling through a medium. So our first wave has the equation a sine kx minus omega t, and then our second one, which is identical, a sine kx minus omega t, and it's only different by this phase here, phi. So to find out the resultant, we just need to add these two together. So we do y1 plus y2. We can pull this amplitude a out as a common factor, and then we have to add together these sine functions. Okay, so you need to be able to add and subtract sine and cosine functions. These trig identities are all provided on the formula sheet, but you need to remember how to use them. So to solve this one, we were adding together two sine waves, so we'll need to use sine A plus sine B is equal to 2 sine A plus B on 2 cos A minus B on 2. Okay, so we've got sine, here's our A, here's our B. We end up with sine of A plus B, When we add these together, we get 2kx minus 2 omega t, but there's only one phi, and we need to divide all that by 2. Then what we need to do to get the number in the cosine function is subtract them from each other. So we do kx minus kx, that cancels out, the omega t's cancel, and we end up with the phi on 2. Doesn't matter if it's positive or negative, as this is a cos function. So now what we can do is just divide through by this 2 to simplify it a bit. And you can see this here is our formula for a travelling wave. We've got sine kx minus omega t plus phi on 2. Our phase has changed a little. This cos phi on 2 is a constant once we've set the initial phase difference between the two waves. And so the 2a cos phi on 2 is the new amplitude for our sine wave. So when we add two waves which are perfectly in phase, the phase difference between phi 1 and phi 2 is 0, so phi is equal to 0, then this cos phi on 2 term is equal to 1. And so this one we can effectively ignore, and our wave has the equation 2a sine kx minus omega t plus phi on 2, which is the maximum the amplitude can be. If we have a phase difference of pi, then this cos phi on 2 term is going to end up as 0. And so these two waves are going to cancel each other out everywhere, and we'll end up with y1 plus y2 0, or a flat piece of string. If phi is some intermediate value, say pi on 3, then we'll end up with the cos of pi on 6. Using our triangle identities, we know is root 3 on 2. So this will be something between minus 1 and 1, and so we'll reflect the amplitude of our sine wave. This diagram just shows you the relationships we just derived. When they're in phase, they add together. When they're 180 degrees or pi radians out of phase, they interfere destructively and we end up with nothing. For intermediate values, we get an intermediate amplitude. Now we're going to consider the interference of sound waves. We've seen that waves interfere constructively if there is a phase difference of 0, 2 pi, 4 pi, or 6 pi, etc. between them. This is equivalent to having a path difference of 0, lambda, 2 lambda, 3 lambda, etc. between them. Because if we consider 2 points which are 2 pi out of phase, there is one wavelength between those 2 points. So here's a question. The lower path, R1 here, is fixed. The upper path, R2, can be varied by changing the height. Describe the relationship between the height and what you hear. Assume that initially R1 is equal to R2. Okay, so if initially we have the same path length here as here, if initially it's in phase, which it is because it's coming from the one source, then when it arrives here it's going to be in phase still because it's travelled the same length, same number of wavelengths, and we will hear the loudest sound. If we move h up to a height h plus delta h, then the path length R2 becomes, okay, initially it was R1, now it has to go up the extra delta h here and down the extra delta h here. And so the path length is R1 plus 2 delta h. Now what we're interested in is the waves arriving here. If there's a difference of 1 wavelength or 2 wavelengths or 3 wavelengths between them, then they will still be in phase and we will get a maximum. So here, maximum sound when the path difference, which is R2 minus R1, is equal to n lambda, any integer number of wavelengths, where n is an integer. And now R2, we've said, is R1 plus 2 delta h, and then minus R1. And so these R1s cancel out. So when 2 delta h is equal to n lambda, where delta h is the change in height, we end up with a maximum. We'll hear a minimum when they are out of phase. So that's when one has travelled some integer number of wavelengths plus a half wavelength more than the other. Okay, at that point one of them's gone like this, the other one's gone an extra half wavelength, so what we're adding together is this, and those will cancel each other out. Okay, so when we have n plus a half, lambda is equal to 2 delta h, we have destructive interference and minimum sound. Final question. Two identical loudspeakers placed 3 meters apart are driven by the same oscillator. So since they're driven by the same oscillator, that tells us that they are in phase. A listener is originally at point O, located 8 meters from the center of the line connecting the two speakers. The listener then moves to point P, which is a perpendicular distance of 0.350 meters from O, and experiences the first minimum in sound intensity. What is the frequency of the oscillator? And we're told that the speed of sound is 343 meters per second. Okay, here's our diagram. Now, when we're at point O, the path difference from this speaker and this speaker is nothing. So that's when they are perfectly in phase. Now, the person at O moves this distance so that now the sound from speaker 1 is travelling path length R1, and the sound from speaker 2 is travelling the path length R2. Now the person moves to position P, and the sound from speaker 1 travels the path length R1, and the sound from speaker 2 travels the path length R2. We're told that this is the first minimum in sound intensity. So what that tells us is that this path length, path difference, R2 minus R1, is equal to half a wavelength, since one must have travelled half a wavelength further than the other to make them perfectly out of phase to give us our minimum. So now all we need to do to find lambda is work out what R2 is and what R1 is. Okay, we can use Pythagoras' theorem to work these things out. So R2, we've got the height here, 1.85, and the length 8. So it's the square root of 8 squared plus 1.85 squared. Taking the square root of that, we end up with 8.21111 meters. R1 is equal to the square root of, in this case we've got the length 8, and the height is equal to 1.15. So it's 8 squared plus 1.15 squared, and that gives us 8.08222 meters. Okay, so R2 minus R1 is lambda over 2, is 8.21111 minus 8.08222. Solving that, we get 0.129 meters. So our wavelength is equal to 0.2579 meters. And now when we're asked to find the frequency, V is equal to F lambda. So the frequency is equal to V over lambda. We were told V was 343 meters per second. So lambda is 0.2579. And that gives us 1,330 hertz, which is equal to 1.3 kilohertz to two significant figures, or to three significant figures, 1.33 kilohertz. That's the end of this lecture. Okay, now a more complicated question. An 80 kilogram hiker is trapped on a mountain ledge following a storm. A helicopter rescues the hiker by hovering above him and lowering a cable to him. The mass of the cable is 8 kilograms and its length is 15 meters. A sling of mass 70 kilogram is attached to the end of the cable. The hiker attached himself to the sling, and the helicopter then accelerates upwards. Terrified by hanging from the cable in mid-air, the hiker tries to signal the pilot by sending transverse pulse up the cable. A pulse takes 0.250 seconds to travel the length of the cable. What is the acceleration of the helicopter? Assume the tension in the cable is uniform. Okay, so in this case, we have a sling here with a mass of 70 kilograms. We have a hiker with a mass of 80 kilograms. We have a cable with a mass of 8 kilograms. And this is being accelerated upwards with some acceleration by a helicopter. Now the forces acting on this hiker are the tension force, which is acting upwards, and his weight force acting downwards. He's attached to the sling and he's also got his own mass, so we should really consider these two together. Now the hiker sends a pulse up this cable. It takes the pulse 0.250 seconds to travel the length of the cable, and the length of the cable is equal to 15 meters. So we can use this to work out the tension in the cable. We know that the velocity is equal to the square root of the tension over the mass per unit length. The velocity is equal to the distance travelled, which is 15 meters over this time. So that's equal to 60 meters per second is the velocity of the pulse. Now the mass per unit length for the cable is equal to 8 over 15, which gives us 0.5333 kilograms per meter. So substituting this in, we have that the tension is equal to V squared mu, just rearranging this, and now that's 60 squared times 0.5333. Solving that on the calculator, we end up with 1,919 newtons as the tension in this cable. Now the total mass acting on the hiker and the spring, mass of hiker plus the mass of the sling times the acceleration, the total force is equal to the tension force, which is acting upwards, plus the mg force, but that's acting downwards, so it becomes minus, so mass of hiker plus mass of sling times g. Okay, now we can solve this to work out the acceleration. So acceleration is t over mh plus ms minus g. So this is 1,919 over 80 plus 70 minus 9.8. Solving that on the calculator, we end up with 3.0 meters per second is the acceleration upwards of the helicopter.